So, of course, if we have measurements for energy and we have heat capacity, we can do calculations, right? Woohoo! So, here's the equation that relates these quantities. Q equals mc delta T. When you write that out, it looks a little bit like MCAT. Q equals mc delta T. If you think of this delta as an A, that looks like MCAT, which is a test you have to take if you want to be a doctor. So what are all these letters? Well, Q is the amount of heat, usually in joules. M is the mass in grams. C is the specific heat capacity in joules per gram degree Celsius. So C is a constant, and they may not give that to you in the problem. You may have to go look it up somewhere. T is the abbreviation for temperature. So this delta, that's the Greek letter D, the uppercase. Delta means change. And it's always the final minus the initial. And sometimes that matters. So the delta T is the final temperature minus the initial temperature. And all the equations and everything is set up because these signs matter. Because we're going to talk about heat coming in and heat going out. And one's a positive and one's a negative. So Q equals mc delta T. That's our equation. So here's an example. You find a copper penny, pre-1982, in the snow and pick it up. How much heat is absorbed by the penny as it warms from the temperature of the snow, which is minus 5 degrees Celsius, to the temperature of your body, which is 37.0 degrees Celsius? Assume the penny is pure copper and has a mass of 3.10 grams. You can find the heat capacity of copper in table 3.4 on page 74. Well, let's go find that before I start writing other things down. Copper is 0.385. So 0.385 joules per gram degree Celsius. Those were the units given in the table. Always write your unit fractions vertically instead of horizontally so that you recognize that gram and degree Celsius are in the denominator. Okay, so there's a lot of words in this problem, right? Why did they throw pre-1982 in there? Well, that's because before 1982, pennies were made out of solid copper. And after that, they started making them out of zinc and just putting a thin copper coating on the outside. So that would affect these calculations. Now, did they really need to go into all that detail? Maybe not, but they did. So pre-1982, we don't really need the year in there. That's extra information. Let's go and identify these other numbers we have in here, though. Here's a temperature, minus 5. And here's another temperature, 37. And then here's another number, 3.10. So, fine, let's write those things down. We've got minus 5.0 degrees Celsius. We've got 37.0 degrees Celsius. And we've got 3.10 grams. Now, it's asking for heat being absorbed, and it's talking about temperatures and masses, and it mentions heat capacity. So we're probably going to need that heat capacity equation, right? So Q equals mc delta T. So we looked up the heat capacity because they told us to do that. What are these two temperatures? We need a final and an initial. What's the first temperature of the penny? Minus 5, because it was in the snow. That's the initial temperature. The final temperature is after it warms up in your hand. So this is the final temperature. And then 3.10 grams, that's the mass. So we're taking those numbers out and we're identifying what they are. The equation has Q, M, C, and delta T. Well, we've got C and we've got M. We need to take these temperatures and make delta T. So I'm going to write that over here down in the bottom. Delta T equals the final minus the initial. So the final is 37, and the minus the initial, which is minus 5. So be careful subtracting a negative there. That's going to end up being 42.0 degrees Celsius. 37 minus 5. Minus 5 is the same as 37 plus 5. What that tells us is the penny changed temperature 42 degrees. So now we can take these values that we figured out. Okay, got my numbers back. We're going to plug these numbers into our equation. Q equals, I'm going to change color here because things are getting kind of messy. So Q, and that's the heat. Well, that doesn't even look like a different color. Q equals the mass, 3.10 grams, times the specific heat capacity, 0.385 joules per gram degrees Celsius, times the change in temperature, 42.0 degrees Celsius. Let's look at our units and see what happens with them. Degrees Celsius cancels with degrees Celsius. Grams cancels with grams. We end up with the unit of joules. Joule is a unit of heat, of energy. So saying how much heat is absorbed. So that's good. We've got an appropriate unit. So 3.1 times 0.385 times 42. And this calculator is telling me 50.127 joules. How many significant figures should that number have? It should have 3. So we can't just look at the number of sig figs in our starting numbers, because these two temperatures were subtracted, and when we do subtraction, they both have 1 decimal place, and so this number, this change, has actually got 3 significant figures, and that's what goes in here. The specific heat capacity was 3 sig figs and the mass, and so our best answer here is 50.1 joules. Any questions? This is a straightforward problem. Here's the equation, Q equals MC delta T. Here's here's M, here's C, here's T, and plug it in. We don't have to rearrange an equation or anything funny like that. This one is not so straightforward. So a lead fishing weight with a mass of 75 grams absorbs 146 calories of heat. If its initial temperature is 47 degrees Celsius, what is its final temperature? So we need to recognize, which should be easy because this is what we're talking about, that this is a problem that's going to require us to use that equation. Q equals MC delta T. It says a lead fishing weight. We're going to need the specific heat capacity, aren't we? So let's go back and look it up. Lead, 0.128 units, joule per gram degree Celsius. So the specific heat capacity is 0.128 joules per gram degrees Celsius. Now, you might not necessarily go look that up first, but it's just easier with this program to do it before I start writing all over the place. Other numbers, 75 grams, 146 calories, 47 degrees Celsius. Let's write those down and figure out what they mean. So 75 grams, what is that? That's the mass. Okay, absorbs 146 calories of heat. What's that? That's Q. And then 47 degrees Celsius. That's obviously a temperature, but is that change in temperature? It's initial temperature. And we're supposed to find the final temperature. Well, here's our equation. Q equals mc delta T. Pardon that. Now, T final is not shown individually in that equation, is it? But what if we solved for delta T? Then we could find T final. Okay, if you like algebra, you can substitute for delta T, TF minus TI, and rearrange it and stuff and go to town. But that's going to get ugly for a lot of people, so we're not going to do that. We're just going to solve this, rearrange this equation for delta T. Oops. Because once we know delta T, we can find the final temperature. So we're going to divide by M and C on this side, so those guys cancel out. That means we have to divide by M and C on that side. So we're going to end up with delta T is equal to Q divided by MC. So let's plug things in here. We've got Q is 146 calories. M is that was the last problem. 75 grams. And C is 0.128 joules per gram degrees Celsius. Let's look at the units before we do the math. Grams cancels grams. Uh-oh. Calories and joules don't cancel, do they? There's a couple different ways we could handle this. We could throw in a conversion factor and convert them right here in the equation, but I don't have room for that. We could just go back and fix one of them and then plug it back in. I think the easiest one to fix is the Q. So here we have Q in calories. Let's convert that to joules. So we're going to divide by calories and multiply by joules. So the calories will cancel out. The relationship is 4.184 joules for every 1 calorie. So that's 146 times 4.184. That is 610.864 joules. That's not a final answer, so I'm not going to round it off there. I'm just going to make a note of how many sig figs it should have. 146 has 3, so this should have 3, which would put the uncertainty in the ones place. Then I'm going to get rid of that original Q up here. I'm going to erase that and write in the one with the correct units. 610.864 joules. Well, that's better, isn't it? The joules cancel the joules. And what about that temperature, just like buried in the sub-basement there? We have 1 over degrees Celsius. That ends up being the same as degrees Celsius. It does 2 flips and comes up to the top. So let's do the math. We've got 2 numbers in the denominator. Be careful. This is how I do it. I've still got the 610.864 in my calculator. Divide by 75. Divide by 0.128 equals. So delta T equals 63 point, I'm just going to throw it should have 2 sig figs, I'm going to throw in 2 extras, 63.63, and that's degrees Celsius. If you do 610 divided by 75 times 0.128, then you have to use parentheses, otherwise you're going to get the wrong answer. Any questions yet? So this is delta T that we just found. I need some space, so I'm going to create some up here. Because we're not done yet, are we? We found delta T. Delta T is the final temperature minus the initial temperature. And we're trying to find the final temperature. So we want TF. So TF is going to equal delta T plus TI. I'm just rearranging that. So I'm going to take delta T, 63.63 degrees Celsius, plus the initial temperature of 47 degrees Celsius. I still have 63.63 in my calculator. I'm just going to add 47. Now the calculator is showing me 110.63 degrees Celsius. I am limited by the uncertainty in that number. Well, I was a little sloppy here. This delta T, the uncertainty, was in the second. There's 2 significant figures. So then, where is it? Up here. It's also in there. So then we're going to round to the ones place. 110.6 is going to round to 111 degrees Celsius. Any questions?
So what up on the top, the TF equals delta T plus TI?
Mm-hmm. Where did that come from?
Yeah.
I took this equation, I'm trying to get TF by itself.
Okay.
So I'm going to add TI to this side to make it go away, which means I add it to the other side. Some of you are good at algebra and you can just write down the rearranged equation. That's awesome. Others of you need to just write every individual step. And it's better to show more work than not enough. Because if you show your work, I can help you figure out where you went wrong. And like when you're working on the online homework, sometimes students will snap a picture of their work and text it to me. That is really, really helpful because then I can look at what you're doing and say, oh, here's this one little thing you overlooked. Because usually it's just one little thing. Any other questions?
Yeah, and how do we come up with that many degrees here?
How do we come up with the sig figs? Okay, so let's trace that back. Here we did a calculation. 146, that had 3 sig figs. We're multiplying it by something with 4, and so this is going to have 3 significant figures. So I didn't round, but I carried that in. So that one had 3. This one only has 2 significant figures, and this one has 3. So then our delta t has 2 significant figures because of the 75. So the uncertainty is in the ones place. Then we take that with uncertainty in the ones place and we're adding 47. This is adding. This also has uncertainty in the ones place. So then our answer has uncertainty in the ones place. This gets a little complicated because we've got adding, subtracting, and multiplying, dividing. You cannot just look at the number of sig figs in your starting numbers and say, oh, the answer's going to have 2. 75 and 47 both had 2 significant figures, and yet our answer ends up having 3. And that's because of those different rules. That's a very good question. Now, you're not going to get hammered on significant figures on a problem like this. But what we need to do is always do our best with the sig figs. Okay? Try to remember them, at least to consider them. Even if you get it a little wrong, give it your best shot and you'll be okay. There will be problems that are specifically addressing, do you know how to do sig figs? A problem like this, they're not going to give you multiple choice exam. They're not going to give you 111 and 110.63 and make you choose between them. Okay?
It seems like most of our temperature answers have came out to whole degrees.
A lot of them will come out to the nearest degree or the nearest tenth of a degree, because it's pretty unusual to measure temperatures more closely than that. Remember we used a thermometer in class, and the digital thermometers measured to the nearest tenth of a degree. That's because most of the time that's good enough. And that one is probably the hardest type of problem, where it asks you to find the final temperature. And then they also threw a conversion of unit in there, which wasn't very nice. This one's a little more straightforward. When 56 joules of heat are added to 11 grams of a liquid, its temperature rises from 10.4 degrees Celsius to 12.7 degrees Celsius. What is the specific heat capacity of the liquid? I'm sorry, I put the word specific in there. What is the heat capacity of the liquid? They're asking us for heat capacity, and they don't tell us what the liquid is, so there's nothing to go look up. We're just going to calculate that using the numbers that we're given. So here we've got 56 joules, we've got 11 grams, we've got 10.4 degrees Celsius, we've got 12.7 degrees Celsius. 56 joules, 11 grams, 10.4 degrees Celsius, and 12.7 degrees Celsius. So what are these things? Joules of heat. What letter is that in that equation? It's Q. 11 grams. That's the mass, so M. Now these guys are obviously both temperatures. This is TI, because it says from 10 to 12. So the final is the 12. Well, we're going to need delta T. Let's just go ahead and calculate that. Delta T is the final minus the initial. So it's 12.7 degrees Celsius minus 10.4. which I believe is 2.3. Yeah, then we've got our equation. Q equals mc delta T. What are we trying to find? We're trying to find C. So we will have to rearrange the equation. I'm going to get rid of everything that's with C. I'm going to divide by M. Those guys go away. I'm going to divide by delta T. Those guys go away. And if I do that on one side, I have to do it on the other side. Gotta be fair. So C equals Q over M delta T. And now we plug in the numbers. So 56 joules, mass of 11 grams, temperature change of 2.3 degrees Celsius. Again, be careful that your calculator is doing what you're what you think you're asking it to do. C equals, how many sig figs should this have? 2. All of them have 2, so 2.2, and then what are the units? Well, they didn't cancel out at all. Joules per gram degrees Celsius, which conveniently are units of specific heat capacity, and that is a reasonable value for a heat capacity. Water is very high at 4, and so pretty much anything else you're going to encounter is going to be less than 4. Heat capacity of 5,000 is just impossible. You shouldn't end up with a negative number either. Any questions? I'd forgotten there were so many of these. Okay, a 328 gram sample of water absorbs 5.78 times 10 to the third joules of heat. Calculate the change in temperature for the water. If the water is initially at 25 degrees Celsius, what is its final temperature? Well, let's analyze this. 328. We got this number over here. Joules. We got this 25 degrees Celsius. What are they asking us for? They're asking for TF, and they're asking for the change in temperature. Here, they're kind of giving us a hint. This is like, I think it was the second one where we were solving for the final temperature. So here they're giving us a hint. Calculate the change first, and then figure out what the final temperature is. So I'm going to do this one a little more abbreviated. Q equals MC delta T. So we're trying to find the change in temperature. So we need to rearrange that equation. We're going to divide by M and C on both sides. So delta T equals Q over MC. Well, what's Q? It's the joules, so that's 5.78 times 10 to the third joules. Always, 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 always write your units in there. What's M? The mass, 328 grams. What is C? Well, we'd have to go look that up. It's 4.184 joules per gram degrees Celsius. I have that one memorized. Sorry, things are getting a little small. I zoomed in too far. We're looking at water. So it's a sample of water. So if you have to look up a specific heat capacity, you need to know what it is. So we go to the table, we look up water, and it's 4.184 joules per gram degrees Celsius. We've written all our units in, and now we're going to make sure that our units are canceling. This type of calculation is one of those instances where if you don't remember the equation, you can just, most of the time, just put the numbers together so the units cancel out, and it'll be just fine. The units can actually tell you what the equation is. So, calculator, 5.78 EE3 divided by 328 divided by 4.184. So the change in temperature is 4.2. How many sig figs should I have? I should have 3. 4.21, and then just out of habit, I'm going to carry a couple extras. So this is where the uncertainty is, 3 significant figures. So it says calculate the change in temperature. Okay, so it's asking for 2 answers. So the change in temperature is 4.21 degrees Celsius. That's one answer. Then it's saying if the water was initially at 25, what's the final temperature? Okay, so there we go, and we remember that delta T is T final minus T initial. The final temperature, we're going to add Ti to both sides. The final temperature will equal delta T plus Ti. So I'm going to take that 4.2117 plus the 25.0. I still have the 4.21 blah 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 in my calculator, plus 25 equals, this says 29.2117 degrees Celsius. And where should I round that? This is to 1 decimal place. So the final temperature was 29.2 degrees Celsius. Any questions? Does that final temperature make sense? The water absorbed heat. Is the temperature going to go up or down? It's going to go up, so that final temperature should be higher. End of chapter 3.